Hello out there and welcome to this video about deadlocks and livelocks. So this is a multi-threading problem that you might encounter, so you at least need to know about it. So we're going to look at a few examples and on both of these. So hopefully you get a better understanding of some of the pitfalls when you work with multi-threading. Okay, so the deadlock is what happens when threads are blocked for further progress. And they are all waiting for each other. So maybe a thread is waiting for one thread. So thread A is waiting for thread B to finish, and thread B is waiting for thread A to finish. So they're both waiting for each other, and that means we're stuck. So they are deadlocked. And nothing happens, there's no progress. The livelock is something slightly more rare, I think, and this is when there's still some kind of progress, something happens, but we just don't get anything done. So that means that our threads are responding to each other. So thread A does something, and thread B responds to that, and based on that response, then thread A responds to that. So they are responding to each other, but they don't actually get to do the job they were supposed to do because they are too busy responding to the other threads. So we are not exactly stuck. Something is happening, but we just don't progress anywhere. So these are the two types of locks that we're going to look at, not to confuse them with the locking mechanism when we synchronize something. So we'll start out with a piggy bank example. I have my piggy bank, obviously could represent a bank account, and you can take money out of the bank. And if I have multiple threads that wants to interact with the bank, obviously I need to synchronize this somehow. I'm modifying my bank, so we need to make sure that I'm not taking money out in two different places at the same time, because then they may both read that there are 100 gold coins in the bank, and then they buy something online to, at a value of maybe 90 gold coins, and then afterwards there will be 10 gold coins left if I have the dirty right that we have talked about a long time ago. And I spent 90 gold coins in two places, but I still have 10 left because we're not updating things correctly. So obviously multiple threads, they modify something, we must synchronize it somehow. Similarly, I can deposit gold coins, and we must also synchronize that. So if you remember the increment counter example, one of the first things we did, I do not want to deposit or get deposits from multiple persons and have some of those deposits disappear because we're overriding. So in this case, I have, Susie and Ben or whatever we might call them, and they are transferring money back and forth between their two accounts. So that's the example that we are going to program. And this here could be the code for my piggy bank. My piggy bank has a balance. There's a string name, who it belongs to. I have a constructor. I can withdraw something from my piggy bank, which means that I'm decrementing the balance by this number of money, gold coins, whatever. And similarly, we can deposit something by increasing the balance by this amount. And then, if I'm not careful, this might be the approach that I do when I want to transfer money. I have a piggy bank that I want to transfer to, and I have how much do I want to transfer. And we just concluded that I need to synchronize when I take something out, and I need to synchronize when I put something in. So I might use this approach. First, I synchronize my own piggy bank. That might be if we are transferring money here, then I'm synchronizing the blue piggy bank. Then I'm also synchronizing the one that I'm transferring to, this one here. I then withdraw the money out of my own account. We take them out and we deposit it into the new account. So that's all good. I have taken money out and deposited into Susie's account. I think I named her that in the example. And we have synchronized everything, so we're making sure that I'm not getting dirty reads and writes and not losing money or overwriting anything. So this might seem like a good approach. Maybe this is all right. So the synchronizing here means that we are locking this object. No one else can modify it or interact with it, at least through synchronized parts. And I'm also locking that object here. Right, so let's see if I actually run this example here. I have my piggy bank. I have so that's what I call it, an unsafe. And I have a child. The child owns what happened? The child has my own piggy bank and not my piggy bank, so this is my thread. And what that thread will do is just transfer a random number of gold coins from my own bank account to the other person's bank account. So the transfer here is just on the piggy bank, and it takes a target piggy bank. Who do I want to transfer to? And then when we run the example, Susie and Brian, I've called them, I make 2 piggy banks. I create a child of Susie, and her piggy bank is A, and Brian's piggy bank is B, and they know about each other piggy banks, so they can transfer money back and forth. Let me just run this here. I should have a printout whenever we transfer something, so that we can see that something is actually happening. Initially, they actually do have 0 balance, but that's not really important for the example here. So we're just going more and more negative balance, but potentially, but that's not interesting. So let's see what happens. Okay, so they are transferring money. We can see that something is happening. But now it seems to be stuck. I'm not printing anything else out. And it's just stuck here. My program is stuck, but it is in a while true loop. New child, so just find my child. It's while true, so it should continue doing this until until I manually stop the program, right? If I just try again here. I haven't modified anything. Why would it need to build here? That's annoying. But okay, so we're transferring money back and forth, and that's going pretty well. So the interesting thing with the multi-threading is that you don't really know when things are going wrong. So it can be really difficult to reproduce these errors. But it now appears that we are stuck again. Right, so I'm trying to transfer money back and forth, but at some point it stops. And the question is then, what happens? So let me just find my presentation again. Here we go. And my trusty laser pointer, there we go. And we ran the example, and this is the code. I've just shown the code twice for the 2 instances of children that we are running, 2 piggy banks. So this is the instance of Susie's piggy bank, and this is the instance of Brian's piggy bank, and we're transferring money back and forth. So the red here indicates a thread running Susie, and the blue here indicates a thread running Brian, and we can see what line of code the threads are executing. And at this point in time, they both want to call the transfer method on their own piggy bank, meaning they're trying to transfer money. Susie is trying to transfer money to Brian, and Brian is trying to transfer money back to Susie at the exact same time. Or maybe not exact, but close to it. So they will both print out, right? And now Susie is synchronizing based on this. So she is locking her own piggy bank. This instance here, she's using the intrinsic lock of her own piggy bank instance. That's what this refers to. So she's synchronizing this, and the lock is now in use. And at the same time, Brian is synchronizing his piggy bank. So he's now owning the lock of his piggy bank here. Now, they both want to synchronize the other one, but as we know, only one thread can own a lock at a time. So Susie owns the red lock here. She wants to also own the blue lock, but that's already owned by Brian. And so they're both waiting until the other piggy bank releases its own lock. Right? So they're both stuck here. Susie is waiting for Brian to unlock, and Brian here is waiting for Susie to unlock. So we have ended up in a case where both of the threads are waiting for the other thread, and nothing happens, and we're stuck. As we saw in the printout, we have arrived at what we call a deadlock. So this is one example of a deadlock. We're stuck because threads are waiting for each other and there are no further progress. All right. Let us look at another example before we start trying to fix this, just so you get a better understanding of what is going on. So here's a very classic old example. I think it's decades old when the thought was first presented. So we have these are 5 philosophers. Right? It's a problem called dining philosophers. And we have these 5 guys, and they are sharing some kind of meal, and between each philosopher is a fork. And these guys, they can either think or they can eat. And in order to eat, a philosopher must pick up both forks. First he will pick up his left fork, and then he will pick up, if he succeeds on picking up the left fork, he will then pick up the right fork. And when he owns both forks, he can eat. And then when he's done, he will put down both forks. And at some point he's done eating, he will put down the forks, and so he may go back to thinking, or he may start eating again. So obviously, because they need 2 forks to eat, they cannot all eat at the same time. Some of them have to think a little bit and wait for the others to put down the forks. So let's assume that these guys are picking up forks, and these guys are thinking, and they're now eating here. So this guy here is eating because he has 2 forks. This guy is eating because he has 2 forks. And this guy, he's eating, well, he's not eating. He's stuck because he cannot pick up his right fork, and you cannot eat spaghetti and meatballs with only 1 fork. So at some point, this guy is done eating, and he will put down the fork, and then this guy can pick it up and start eating. So that's sort of the idea, that they are eating and they are thinking, and they have to have 2 forks to eat. But what happens if they all want to eat at the same time? They all reach out for their left fork, like that, and they must now all pick up a right fork to continue, or at least wait until a right fork is available. But this guy will only put down his left fork when he's done eating, and he's waiting for that guy to finish eating, which is waiting for that guy to finish eating, and so on. So they're waiting for each other all over again, and we have there's no progress. They're all just sitting with 1 fork in their hand, and they're waiting for someone else to put down their fork, and they're going to wait forever. So we have ended up in a deadlock once again. So another example of how things can go wrong if we're not careful about how we lock things. So I also have this as an example. So let's just try and run. All right, let's take a look at the code first. So I have defined a fork. I'm giving them numbers just so I can keep track of what's going on. So I have 5 forks. I have 5 philosophers, famous philosophers. You might know them. And Socrates, he knows about fork 1 and 2. Plato knows about fork 2 and 3. Emmanuel 3 and 4, 4 and 5, and 5 and 1. So they both know about a fork that's to their left and to their right. Just like we saw in the example, right? This guy knows about fork 1 and maybe fork 1 and 2. This guy knows about fork 2 and 3 and so on. For each of them, I put them in a new thread and then I call start. So let's see, what does a philosopher do? He knows about 2 forks, he has a name, and this is it's a bit much to go through. So while true, so until the end of the time, I guess all of them, these guys are dead, so they're just sitting in heaven and eating spaghetti and thinking. And I have a random, so either this is 0 or 1. We do one thing or the other. So we first we print out the name he wants to eat. He will pick up his left fork. Then we print out left fork is picked up. We will then pick up the second fork, and we're now eating. And eating takes a number of milliseconds, and I don't really need this one or that one. Right, and at some point he's done eating, he will put down his left fork first. Oh, he will put down his second fork, the right fork, and then we start over and we check again, should we eat or should we think? If we're not eating, then we're thinking, and we don't require any forks for that or anything else. So we're just thinking for 10 milliseconds. Right? It takes more time to eat than to think. So that's the idea. Pick up for left fork, then right fork, put down left fork, then put down right fork. Let us check out the fork, because the pickup here is the interesting part. Right? You will notice that I have used a guarded block here. So a fork has a number and it knows whether it's in use or not. And if it's in use, then it waits. So if a philosopher is trying to pick up a fork that is in use, then that philosopher will wait. I don't need that. Cleaning it up. If he's trying to pick up a fork that is not in use, then that fork will become in use. So that's fine. So the point is that the philosopher might be stuck in this while loop waiting for a fork. At some time he put down the fork, and then it's no longer in use, and we're notifying everyone, hey, this fork is no longer in use. So if any other philosopher is waiting for that fork, they can now pick it up. So that's the idea. And let's run the example. We should hopefully get a lot of printouts that they are eating and thinking and eating and picking up forks and putting them down again. So let's see. And we actually, we're already stuck. So they're all thinking and someone wants to eat, and they're picking up fork 1 and 3 and 5 and 2 and this one. So each of them actually picked up a fork. Socrates, Emmanuel, Søren, Platon, and Carl, they all own a fork now. Maybe I should have printed out that someone wants to pick up a fork. But yeah. So they're stuck. They each have a fork. They're waiting until someone else puts down the fork, and we have we are arrived at the thing where they. Oh, not that thing, but this case here, where they are each holding a fork and we're stuck. Okay, so we ran that and we move on to the next part. We saw that we ended up in a deadlock because they all want to eat. They all want to eat at the same time. So the question is, how do we fix it? And there's no sort of one approach to fix all. Your specific deadlock might require a very specific solution. We're going to think up a few approaches to the philosopher problem, and the easiest one will actually not work in most cases. And we will also try to fix the piggy bank, which is a more general approach, so that might be reusable across multiple problems. So the easiest one is to let one philosopher be opposite-handed, so he's going to pick up the right fork before he picks up the left one, unlike all of the others. And if we do that, right, why would that work? Well, we still have this, oh, not that one, but if this guy does not pick up left fork, but he wants to pick up the right fork first, then he will see, okay, that's already in use, so I cannot proceed, so he will not pick up any forks at all, and the left fork will be okay. It will be free, and this guy can then pick up the left fork, he can eat, put down his right, and then that guy can pick up left fork, and he can eat and put down the right one, or left one, right, and so on. So this is a fairly simple solution. We just make one of them right-handed instead of left-handed, and we can actually just try and do that. And I will just do like this. So I'm just swapping the forks around. He's now, this is his left hand, this is his right hand, and we just, this is the order he picks up the forks, you might say instead. So he wants to pick up fork 2 before fork 1. And if I run this, and well, here's the interesting part, that because it's multi-threading, it's a bit random when it gets stuck, so we might have to wait forever to conclude that this is not actually getting stuck in a deadlock. So it's running and running, and I'll just keep it running while we continue the presentation here, and then we go back and see that they are still thinking and eating and whatever they want to do. So that's the quick fix, and that's very philosopher specific. There were no left or right hands in the piggy bank. We might add some kind of timeout, saying if a philosopher has waited for some seconds or milliseconds without being able to pick up the second fork, he will then put down the first fork and either try again or think instead. So now he's not stuck anymore. He will just say, okay, I've waited too long, maybe I'll just skip eating this time around. And the third one is to have some kind of external, I don't know if that's a food director or waiter or something, and that class should then be able to identify the deadlock and tell all the philosophers that they must put down the fork and sort of reset and then try again. This one is a bit more difficult. How do you detect the deadlock? So it's I don't know, maybe this is a philosophical idea. We're not going to go into specifics here. But we could have this third guy, which is actually what leads us to the livelock later on. But we have some kind of observer or monitor thing that keeps track of whether they are in a deadlock or not. Alright, so we fixed the philosophers example pretty easily, and we can fix the piggy bank with this thing here. They are using, well, currently they are using the intrinsic locks of the piggy bank, but if we introduce lock objects, there is a try lock method, which you have probably seen before, and we can use that to attempt to lock an object. If that locking fails, then instead of just waiting until it's free, the lock, then we can do something else, or we can just release all our locks and then try again a few milliseconds later. So the idea is that instead of just saying I want that lock and I'm going to stand here and wait until I can get it and not move anywhere, we will instead say I want that lock. If I cannot have it, okay, I'll wait a bit and then I will try and ask again, can I now have that lock? No? Can I now have that lock? So it's a bit like your backseat children that asks, are we there yet? Are we there yet? Is the lock free yet? Is the lock free yet? So let's look at the other one. See, they are still eating. That's wonderful. I am now confident that I can conclude that it actually works. I don't want to keep this running. And they're eating so fast they cannot stop. There we go. Okay. What? Nope. What did I do? Show toolbar. There we go. Okay, so we will go back to the piggy bank. I actually have a working version. Piggy banks run unsafe. We'll try this thread safe piggy bank. So my children has not changed. They are still just transferring money from mine to their, not mine, not random number this time around, but that's not really interesting. We started the same way. A child, Susie knows about her own and the other, and Brian knows about his own and the other. And we move on to the safe piggy bank, and there's a balance, which is updated, yeah, but it's never accessed, so okay, that's why we complain. And so this part is sort of the same thing. I have a lock object now. So you will see that when I don't synchronize anymore down here in the other one, unsafe, nope, this one, I would have the synchronize based on this. So that means inside this block, I'm now owning the lock of this. And inside this block, I'm now owning the lock of 2. But in the thread safe piggy bank, there's no synchronized. We use the lock here instead. So I have a success, and while there's no success, then we keep trying. So first, I will try to lock my own, and this method call will return true if I am able to lock and acquire this lock, and if not, it will return false, which means that we just sleep for 1 millisecond and then try again. We then try to get the lock of the target piggy bank, and we try to lock that one. And if we do not succeed because that's already locked, then we return false here. We do not go into the if statement, and we just unlock. We have to manually unlock the one that we locked up here, and then we sleep for 1 millisecond. We'll try again. If we successfully manage to lock both piggy banks, we withdraw the money and we deposit it. We remember to unlock the target piggy bank again. We say that we actually succeeded, and then we unlock our own piggy bank, and then we are done with the transfer. So we may potentially have to try many times here, but at some point we will succeed, and at no point are we waiting for the lock. Either we acquire the lock, and that's good, or we do not acquire the lock and we wait and try again later on. So if I were to run this one here, again, a bit difficult to verify that this actually works, because it works when I don't get any errors forever, and we will see that it's already run further than what my unsafe piggy bank was able to do. So they're just sending money back and forth, and I will conclude that this now works. Right, but again, fairly difficult to actually verify if you have to run for an unknown number of hours for this to work. So you'll have to either write your code as simple as possible, or there are some external tools to sort of evaluate these kind of things, but that's outside of today's session. So we fixed the piggy bank, and our approach was we try to lock the source, then we try to lock the target, and if we successfully lock both, then we do the transfer. If either of these try to lock fails, then we wait and try again. So this is the sort of general approach. You try something, if you don't succeed, you wait and try again. And I have the code which we saw, so I'm going to skip that, and we go down to this slide, a blank slide, I guess. So that was all for the deadlocks. We've seen two examples. The piggy bank was a more general approach to the solution, but the basic idea is the same. You have multiple threads that are waiting for other threads to finish their job, and the other threads are waiting for the first thread to do its job. So they're waiting for each other, and they're deadlocked, and there's no progress. They're stuck. So the second topic here, the livelock, is when things do happen, they're not entirely stuck, but there's no progress. So that might be if in the piggy bank I always succeed in locking the first lock but not the second, then we keep trying, we go over and over, so things happen, but we never really succeed in doing the things that we wanted to. I have another example here, you might have tried it out. So these guys are now reacting to each other. They're trying to move along, but they're reacting to each other. This guy moves up, this guy moves down, and so on. And they are always right. They're moving back and forth, but they're stuck. There's no progress here. So a very simplified livelock example. I have another one. This is from the Java documentation actually. This guy, this time we have Terence and Philip. They're eating soup. They have to share a spoon again. I don't know what's up with all the sharing of the spoons and forks, but we're sharing something, right? And the idea is that you can pick up the spoon and you can eat the soup, and you can put down the spoon when you're done, and then the other guy can pick up the spoon. And in those, these Corona times, you shouldn't do this at home, but just for our example's sake. Now, as you may know from South Park, Terence and Philip are Canadians, so they're super polite, and that means if a guy picks up a spoon and notices that the other guy has not eaten first, he will put down the spoon, or he will hand over the spoon to the hungry guy and say, "Here, you go first." So that's the idea, right? He picks up the spoon. He figures out, hey, this guy, you haven't eaten. Maybe you should go first. So he hands over the spoon. That takes some time. And this guy is about to eat when he notices that this guy hasn't eaten anything. So, being a polite Canadian, he'll say, "Why don't you go first?" And then we're back again. He will notice, hey, you haven't eaten, hand over the spoon. So they're just handing the spoon back and forth. There's no progress, even though things are happening. So they are too busy reacting to each other to actually progress anywhere. So that's our setup. They're eating the soup. They have one spoon. They're super polite. So they, if a friend or person or guy, whatever, these guys are friends, I guess. If one of them picks up a spoon but notices the other friend hasn't eaten, they will hand over the spoon. And then they just keep handing the spoon back and forth, and no one ever eats. That's what we see. And if we were to implement this program or the example, we'll just quickly go over it. This is the friend class. This is what's happening. We have a friend with a name, and he is hungry initially. We can get the name, and we can get whether he's hungry. And we are running this in a thread. So as long as he's hungry, he will perform this behavior here. He knows about a spoon, and he knows about the other friend. So I have two instances. They both know about the same spoon, and they both know about each other. And as long as we're hungry, we will first check, do I already own the spoon? If I don't own the spoon, then we will sleep for a little while, and then we will go back over again here. If at some point I do own the spoon, then we don't go in here. We check, is the other friend hungry? Which in that case we say you go first, and then we set the owner of that friend, and then the continue keyword, we start over. We don't execute the rest of the while loop. We just start over here. And then at the end here, we actually use the spoon, and we say now we've eaten, we're no longer hungry, and then we can give the spoon over to the other friend, and we will stop here. So initially the spoon is given to one of them, and if I were to run this, one of them would check, okay, I'm not the spoon owner, I don't have the spoon in my hand, so I will just sleep and start over. The other guy will see, the one who actually initially owns the spoon, he will see, okay, I do actually own the spoon. Then we check, okay, the other guy, he's actually hungry, so let me set the spoon to hand it over to him. And then the other guy will see, okay, now I am the spoon owner, so we go back. So this is the part where they keep going back and forth. So we are stuck in a livelock because we never reached the bottom part down here. And we'll just skip all this explanation. And I could run the example, but no, we'll skip that. So the question is, how do we implement these livelocks? Or, well, not intentionally, but let us assume that all the philosophers were able to detect the deadlock, and then they can all react to it. So they would all pick up the right fork, they all detect the deadlock, they also reset by putting the fork down again. The deadlock is resolved, but now they all want to pick up the fork again, and so we're back in a deadlock, and so we go back to step 2, where they detect the deadlock, they resolve it, they reset, they put down the fork and pick it up again. So if we're not careful when we try to solve a deadlock, we might introduce a livelock instead. So just a small pointer. So these are concepts that you should know about. Unlike the other topics, there are no exercises in implementing the deadlock. This is not something you want to implement, and you just need to know about it. In most of your semester project systems, I can't imagine that you will run into a deadlock. So you have to have some fairly complicated multi-threaded program to introduce these usually. So it's just concepts that you have to watch out for and that you have to know about. And this concludes the video. So thank you for watching.